Okay, so as we study properties of quadratic functions, the parabola, let's take a look at this little video here once again. And again, this video kind of maps out positions of different projectiles. So launched at different angles. But the important thing is that these are mapping out parabolas. Okay? So we have the blue parabola is a nice one. As the launch angle gets higher and higher, what happens to the parabola as the launch angle gets higher? Well, between a 0 launch angle and 45, the parabola looks to be, it goes farther down the, oh, there we go. Let's see if I can try this again. Oh, beautiful. Okay. So the parabola seems to be getting narrower as the launch angle goes up. Now watch, this little yellow one right here, that would be a part of a pretty wide parabola, wouldn't it? It looks like this one's not as wide as this one. But actually, this parabola would be the very tip, the very top slice of a really wide parabola. And this one would be a parabola that's more narrow. They're all opening down, but we would have parabolas that would be kind of getting narrower and narrower, and this sort of yellowish orangish one here is the narrowest. Does that make sense? Okay. Does anyone know at this point what part of the quadratic equation dictates how wide or narrow it is? Do you remember? A. Yes. A is absolutely correct. Okay. Okay, good. So we know something. All right, that's good. All right, so as we look at these two diagrams, now let me explain this, okay? This right here is a strange object, but you're going to notice here, and again, I got this picture off of YouTube. There's actual video here, but this is sort of a side angle. We have two parabolas. And this has been rotated to the side a bit, so these do not look perfectly symmetrical because it's a bit of a side. But I like this version because the parabola is one of several. They're called conic sections. Okay. Now, in high school math, we don't study this anymore in high school math. It's sort of left more for university now, but we used to study this in high school. Equations and graphs and things of conic sections. Some of the conic sections were a circle. Envision this. If you take this blue slice and you slice it parallel to the base, you're going to slice this cone and it's going to make a circle. If you slice it up and down like this one, it makes two parabolas. And so circles, parabolas, ellipses, hyperbolas, those are conic sections. And parabola is just one of them. So you can kind of think of two cones, meeting together at the one point there in the middle. And if you slice them different ways, you get kind of different shapes of their cross sections. And the parabola is one of them. All right, so a vertex. We talked about a vertex already before. So it's the max or min point on a parabola. Okay, so it's the tip. Here's the vertex right here. Here's the vertex right here. Okay, and so you can draw that picture to support that if you want. Okay, what else do we need to talk about? Axis of symmetry. All right, so if you look here, remember I said that a parabola is symmetrical when you draw a line through the vertex. And so the axis of symmetry would be the vertical line that passes through the vertex. Okay? And it's what sort of cuts the parabola exactly in half. So the axis of symmetry, vertical line that passes through the vertex. Okay? And you usually write the axis of symmetry, because it's a vertical line, in the form of x equals. Okay? So it's going to be a vertical line. It's going to be x equals, and it's going to be the y value, the x value of the vertex. Y. So x equals, and I'm just going to put in here x value of the vertex. So that's the form of the equation there. So x equals, I'll put this in brackets so it doesn't look so funny, whatever that x value is of the vertex. Okay. if we go back to this, this little diagram right here, I'm just going to clip this into my notes here. Just give me a second. Okay? So if we go back to this right here, I'll plop that right here. So on these parabolas, okay, the vertex, let's see if I can, the vertex would be right here. That's the vertex. Vertex, 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 vertex. Okay, you see that? Now, the equation of the axis of symmetry would be the vertical line that passes through the vertex. So let's say that this right here is 0, 0. That's the origin right there. So the x value of the vertex would be the axis of symmetry. So let's just say that this point was, let's say, 3, 8, this vertex point. Well, the axis of symmetry, and sometimes I abbreviate it just AOS, axis of symmetry is x equals 3. Okay? That's the axis of symmetry. Okay? Questions there? Is that a question or is that a stretch? A yawn and a stretch. Okay. No question. Okay. All right. So we talked about a minimum value as part of the definition for the vertex. So the minimum value would be, the maximum value, sorry, would be the y value of the vertex for a parabola that opens what? What's the blank there? Down or up? Down. I have a down. Any other votes for down or arguments for up? Okay, if it's a maximum value, it's going to be a parabola that opens down. Right. Okay. So, good. The y value of the vertex for a parabola that opens down, I'm going to say downward. That's usually the wording we use. Okay. Underline those. Okay. So it is important to note here. So these parabolas all open downward, and this would be the maximum right here. So it would be y equals, in this case, 8, because that's the y value. Okay. And the minimum value, of course, would be very, very similar, but it would be the y value again of the vertex for a parabola that opens upward. Okay. So here's the video of the conic sections. It doesn't look like it's moving very slowly, but so if you take a look at this here, so there's two cones, all right? And in this video, they're going to show you sort of what the conic sections are. Now you see you have this green sort of plane. It's cut and it's parallel to the base of those cones, and that is a perfect circle. You see that? So a circle is one conic section. If you slightly put that section on an angle, you have what? You guys know what that's called? Ellipse. Very good. Yes, that's an ellipse. Okay. Now, if we bring this, let's see, what are they going to do next here? Okay. Okay. So they're bringing this up here now, so it doesn't go all the way through. It looks like that. What does that look like? Okay. That kind of looks like a parabola. Yeah. Yeah. That kind of looks like a parabola. And if we move that up again here, you get the diagram that we had. We have first there. Okay. All right. So there you have it. That's kind of what a parabola looks like. It doesn't look like a U. It's not a U, and it's not like this, right? It's not. Doesn't have a corner. It's rounded. Have you ever seen at football games or sporting events, even on TV, where they have the guy with the big headphones there, and he's got the dish. He's got that big microphone, and he's on the sidelines like this, trying to get the sounds of the game or whatever. Have you ever seen that? Okay, so that dish would be a parabolic dish. And the neat thing about a parabola, and this is a bit of a physics, you study this in physics a bit more, but the neat thing about a parabola is that there is a point right here, somewhere in the middle, it's called the focus, that when you have sound waves or light waves or anything coming in, parallel to the axis of symmetry, they bounce off the parabola and they bounce to this one single point, no matter where they come in. So that's kind of a neat thing, and that's why the parabola is used for these microphones and stuff. So let me just kind of try to draw a parabola here. So if that's a parabola, any sound wave or light wave that comes in parallel to this axis of symmetry, okay, I'm going to do my best parallel lines there, then there is a point right here on the axis of symmetry where these will bounce towards. And they will all end up at the same spot. And so that's why in a parabolic dish shaped like this, and we have a microphone or something right here. Do you know where else this is used? Parabolas? Boys, are you listening over there? Where else are parabolas used? Sorry? Was there a guess over there? Okay. If we have a parabola sideways, you all came to school in one of these today. A giant mouth? Nope. And a car, yeah, okay, most of you came in a car today. And guess what? We have a light bulb right here, and the light emanates light in all directions, and guess what? The parabolic design of the light sends the light waves parallel to each other out like this. It's a headlight. Okay, that's why headlights are so focused, right? And of course you have these ones that don't hit the parabola that go out like this too. Okay, so you have sound waves coming in for a parabolic microphone. You have light waves emanating from the focus out parallel too. Okay. Yeah, it could look like something else. What are you saying? Looks like a what?
It looks like UFO.
A UFO, okay. Or a comet or something, right? Ooh, okay. All right. All right, what else do we know here? Let's see. Okay, let's take a look at this, guys. So x equals 12.5. What is this referring to right here? Axis of symmetry. Very good. What is this point right here? 12.5 comma 18.7. What's that? Vertex. Very good. Okay. Okay, does this parabola have a maximum?
Minimum.
Okay, it has a minimum. Does it have a maximum?
No.
No, it doesn't have a maximum actually. Now let's talk about that. Do you see these arrows right here? Shh. Boys. You see these arrows right here? That means this graph continues on forever. Up and outward. So it does not have a minimum value for the x. It goes forever to the left, even slowly, and it doesn't have a maximum value on the y. It goes up forever as well. Okay, so that's important to note because a lot of students think, well, this is the maximum x value right here, and this is the minimum x value right here, and this might be the maximum y value. But no, those arrows say they keep going forever and ever. Okay, so there's no max value there. Okay. All right, so let me just pause and show you this right here. Okay, how do you know what the x value of the vertex is, or the axis of symmetry, if you're not given the vertex? So here's a way to find this. Because the parabola is symmetrical, okay, and I'm just going to clip this so I can write on it a bit here. Because the parabola is symmetrical, we can use that to our advantage here. So kind of looks like this here. And because if you take a look horizontally, like at the x-axis here, you have this point and this point, right? You also would have this point right here and this point over here. And because the parabola is symmetrical, that means that the axis of symmetry has to be exactly between all of those points that are on a horizontal plane. So this point and this point, that is -2 over here and +1. So what is exactly between -2 and +1? Well, what is it? That's 1, 2, 3. So half of 3 would be 1.5, so you can either add 1.5 here or you can subtract 1.5. Okay, what you need to do is find the average values of the x. So let's say this is 2, and this is going to be what? 3, 4, 5, 6. That's 6 right there. Okay, so to find the average of the two, you would add them. So 2 plus 6 over 2, right, is 4. So 4 is the actual middle point there, and that's the axis of symmetry. So find the average. So add them divided by 2. If you wanted to find the half of the distance between the two, then you would subtract them divided by 2. So to find the actual midpoint, x equals a, we'll add them divided by 2. All right? Okay, any other questions here? Guys, look through the lesson and see if there's any examples or any definitions that you are wondering about before we move on.
Okay. Are you guys preparing something?
Mm-hmm.
Just to prepare something.
Yep. Yeah.
No, I didn't write it down. I'm thinking it is, I don't know. Mr. Maxwell, can you show us the assignment?
I will in a second, yeah.